In this video, we're going to evaluate exponential expressions using the product rule, the power rule, and the quotient rule for exponents. We're also going to take a look at the power rules for products and quotients, and then define a number raised to the zero power. We're even going to take a look at negative exponents. So really, we're going to look at all of the exponent rules in this lecture. First, let's take a look at a couple review questions. I'd like you to evaluate the following. Several times through this video, it'll be helpful for you to maybe pause and give the question a shot, then push play to see how you did. And for these several review questions, that would be a great idea to go ahead and get started by pausing, trying these four, and then push play to see how you did. Negative 4 squared. What this really means is negative 4 times negative 4, which 4 times 4 is 16, and a negative times a negative is a positive. So because the negative sign was inside the parentheses, that was squared, meaning the whole parenthesis times itself. That's very important. Down here in number 2, 4 times 4 is what's going on, which again is also a positive 16. If the question had said negative 4 squared, that one would be the opposite of 4 times 4. Only the 4 is squared, not the negative. So 4 times 4, still 16, but this is how we would get a negative 16, by not having the minus sign inside a group of parentheses. Example 3 here. Negative 4 times itself 3 times. The negative 4 times the negative 4 we have done in example 1, that's positive 16. That times a negative 4 is now 64, but there was one negative times one positive, so negative 64. If the exponent is odd, and we are raising a negative to that power, so a negative number raised to an odd power, the answer will be negative. If we have a negative number raised to an even power, we will get a positive answer. In example 4, we have 3 times 4 squared. So this is 3 times 4 times 4. I know 4 times 4 is 16. We've done that several times in this exercise so far. And 3 times 16, then 48. Hopefully you did okay with these review questions. 5 through 8 also review. I would like you to label the base and the exponent in each of these. Go ahead and pause the video and try these out. Once you believe you have the answer, go ahead, push play, and check to see if you got that correct. The base is the 3, the exponent 2. In the power, the power that we're looking at here, 3 squared. If that would just go away, that would be wonderful. There we go. 3 squared is the power with a base of 3 and an exponent 2. If you're familiar with cheerleading, we think the base is still the same thing, and the base holds the flyer. In cheerleading, the exponent would be the flyer. The base is still the base, the thing holding that exponent. As I look at example 6 now, the base is still 3, the exponent 7. The negative is not raised to the power, so that is not included as part of the base. In number 7, likewise, similar to example 6, 5 is not raised to the power 2, only x is. So x is the base, the exponent 2. In number 8 now, because of the parentheses, the base is -4, and the exponent is 3. Again, on these review questions, hopefully you did okay as you checked the work that you've done. Now we're going to get into each of the exponent rules and work through some examples in isolation, and then we'll combine them all together at the end. The first exponent rule that we will explore is the product rule. If we have the same base, a and a, but raised to different exponents, here m and n, and we're multiplying. If we multiply the same base, we will add exponents. Let me show you why that works. X to the 5th, 1, 2, 3, 4, 5. X to the 5th is x times itself 5 times, and x to the 10th, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. X times itself 10 times. If I find out how many x's I have so that I could write x to 1 power, we add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 5 plus 10 equals 15. In the next example, I'm not going to write out the problem exactly the same as we did the first. Instead, I'll do this more as you will commonly work through a problem like this. Okay, 2a to the 4th times 3a to the 5th times 4a to the 6th. What's happening here is we're going to take all of the coefficients, 2 times 3 times 4, and then all of the exponent or the variables now together, a to the 4th times a to the 5th times a to the 6th. Since it's all multiplication, again, we're going to multiply the similar factors. 2 times 3 times 4 is 24. A to the 4th times a to the 5th times a to the 6th. We're going to add exponents since the base a is the same in each. So 24, a to the 4 plus 6 is 10 plus 5, 15th. The quotient rule is, again, same base a, raised to 2 different powers, m and n. If we're dividing the same base, we're going to subtract exponents. Before we multiplied the same base, so we added. Now if we're dividing the same base, we'll subtract exponents. Again, let's take a look at the details of what's going on here as to why this works. A to the 10th, a times a, 2, 3, 4, 5, 6, 7, 8, 9, 10 a's divided by a to the 6th. 1, 2, 3, 4, 5, 6. And if we divide now like terms, a divided by a, or the common factors, a divides by a to be 1, a divides by a to be 1, a divides by a to be 1. Again, 2 more times. We're left with 4 a's in the numerator. A to the 4th is the final answer. And if we were to have just applied the rule, it would have been a to the 10 minus 6, which equals a to the 4th. Now when we get to an example like 2b, things start to look a little bit more complicated because you have different factors, different bases of c and d, plus there's a coefficient. I like to look at this as 3 separate fractions. So negative 35 21sts times c to the 4th divided by c to the 1st times d to the 10th divided by d to the 1st. Now we can apply the exponent or the quotient rule where there is where the bases are the same. So for C and for D, I'm looking at C to the 4 minus 1 times D to the 10 minus 1. For the coefficients, we're not subtracting 21 from 35. Instead, we'll divide this just as we would have simplified a fraction in the past. So we see that 7 divides evenly into 35 and into 21. Into 21 3 times and into 35 5 times. So we have negative 5 thirds times C to the 4 minus 1 times D to the 10 minus 1. This is going to give us a final answer of negative 5C cubed D to the 9th divided by 3. The next exponent rule we'll take a look at is the power rule. Here we have a power a to the m raised to an exponent of n. And we'll read this a to the m to the n power. We're going to multiply exponents in this case. And what I like to think of is almost a distributive property, where if I had like 2 times x plus 4, what's being separated by the parenthesis is the coefficients. So 2 times 1x and 2 times 4. We know to use multiplication because of the parentheses. In this property, the same. This time the exponents are separated by parentheses, and so that helps me remember that I'm multiplying the exponents here. The next property we look at, it's going to be there's going to be like another layer that can sometimes be confusing. So at this point, let's just understand the exponents are separated by the parentheses. We're going to multiply the exponents. So b to the 10th to the 7th will be b to the 70th. And again, let's look at why this works. b to the 10th times itself 7 times. Six, 7. Okay. Earlier, b to the 10th, that's 10 b's. And there's 7 groups of those. Well, if I was to write all of them out, 10 b's, another 10 b's, another 10 b's, all the way, and I counted them all up, there would be 70 of them. This is more of a visual way of looking at why the product rule works. In example 3b, I don't want you to actually evaluate. We're going to pretend like 12 is a variable, because a number could be a base, and this is the first example looking like that. So 12 to the 9th to the 4th power is going to be 12 to the 9 times 4, or 12 to the 36th power. The next is going to be the product of a power rule. This time, I have a times b. There's a product, that whole thing being raised to an exponent. Similar to that distributive property example, I have to raise each of the terms, or the factors, a and b to the m power. And we have a to the m times b to the m. This gets somewhat confusing when there is a coefficient or just a variable without a exponent written. In this case, a, b, they're both raised to the first power. And what was being multiplied was the exponents. So m times 1 and m times 1 was a to the m and b to the m, final answer. It was not m times a and m times b. This you will see in example B, maybe more so, where folks can sometimes run into some issues. So for here, x to the 15 and y to the 4th power, we're going to raise that whole thing to the 5th power. So each of those exponents will be multiplied by 5, and I have x to the 75th power times y to the 20th power. In example B, I have negative 2 to the 4th. So here a negative to an even power is going to become positive. 2 to the 4th power, not 2 times 4, but 2 to the 1st to the 4th. And so the 4 times the 1. A to the 9 times 4. B to the 7 times 4. And ultimately we can simplify 2 to the 4th power is 16, a to the 36th, b to the 28th. Final answer. The product of a quotient rule. This time I have a quotient, and this actually is the power of a quotient. This was wrong here. This should be called the power of quotient rule, because I have a quotient raised to a power, raised to this exponent m. And just like before with the product of a quotient rule, we're going to take m and multiply it by the exponent on a, which is 1, and the exponent on b, which is 1, giving us a to the m divided by b to the m, as long as b is not equal to 0. Because remember, we can't have 0 in a denominator, or a denominator of 0. So now using the quotient rule, a to the 2 times 9, or 18th power, divided by b to the 3 times 9, or 27th power, is our answer there. And in example B, negative 5 to the 3rd power. This is a negative to an odd power, so it's going to stay negative. Negative 5 cubed times g cubed divided by 6 cubed times h to the 10 times 3, or 30th. 5 cubed is 125, so negative 125 g cubed divided by 6 cubed which is 216, h to the 30th. The negative exponent rule, I kind of think about vacation. So I usually ask my students, I say, who has heard of someone saying, I need a vacation? You yourself may have been that person. Would you describe their mood as being positive or negative when they say, I need a vacation? often when someone is at that point that they're expressing a need for a break. They're in a negative kind of mood. And most people here in Baltimore will go down the ocean to Ocean City for vacation. And when they're on vacation, they become positive. Their mood gets better. Personally, I like going to the mountains. And so if I was in a kind of negative state and needed a vacation, I would be going to the mountains to become positive. B to the first. Four to the negative third. Because of the negative 3 exponent, this becomes 1 over 4 cubed. We're going to bring the factor to the denominator, and that will create a positive exponent. That does not change the sign on 4. So if 4 was negative, the negative stays attached to the problem. And if it were, if the 4 was to move, only the exponent becomes positive with the negative exponent rule. And 4 cubed is 64. So our final answer, 1/64. In 7b and c, we see addition and subtraction signs. So we're going to treat each individual term now separately and simplify using the negative exponent rule. So I have 1 over 2 to the first plus 1 over 3 to the first. In order to simplify this further, we have to add the fractions. And remember, to add fractions, we need a common denominator. The least common denominator here for this problem is going to be 6. So I will multiply, I will multiply this first fraction by 3 over 3. This is sort of a magic 1 because anything divided by itself is 1, and it will create a denominator of 6, which is what we desire as we take 3 times 2. 3 times 1 is 3. So I have 3/6 plus, and over here we'll multiply by this magic 1 of 2 divided by 2. The denominator is now 6, and the numerator is 2. I can add the numerator. 3 plus 2 is 5 divided by 6. And in the last example, C, 5 to the 0 power. Anything to the 0 power is 1. And let's talk about that just for a moment here off to the side. Anything to the 0 power is 1. Anything to the 0 power. If it was like this, actually only the g is to the 0 power, and so this would equal anything. Where if we had anything to the 0 power, that would equal 1. So whether it is, 142,000 to the 0 power, still going to be 1. Back to our example, we're subtracting now 5 to the negative 1 power, or 1 over 5 to the first. Negative exponent becomes positive when I move 5 to the first to the denominator. We subtract now, the 2 is negative, so 1 over 5 squared. 1 over 5 squared, 5 squared is 25. And we now need a least common denominator. That least common denominator is going to be 25. So everything will be multiplied by, every term is going to be multiplied by the missing portions or missing factors in the denominator. The second one is going to be multiplied by 5 over 5. The first one will be multiplied by 25 over 25, which will give us 25 minus 5 minus 1 all over 25. 25 minus 5 is 20 minus 1, 19 25ths is the final answer to this question. Example 8, we just want to simplify this with positive exponents. X to the negative third, x to the negative 7. Because of the negative exponents, we're going to move the factors to the numerator or denominator so that they'll be positive. So we have x to the 7th over x cubed. Thinking back to the quotient rule, we've got x to the 7 minus 3, or x to the 4th power. Another way to do this problem would be right away to subtract, so x to the negative 3 minus negative 7, which is going to be negative 3 plus 7, which still gives us x to the 4th as that answer. As I look at example B, this entire product, 2 times x cubed, is being raised to the negative 4th power. So that's going to all move to a denominator. 2 to the 4th positive, x to the positive 12th, now 2 to the 4th is 16, so 1 over 16x to the 12th for our final answer. Here's a summary of each of the exponent rules that we've discussed. The product rule, if we multiply, this actually should be an A. So if we multiply same base, a to the m times a to the n, that is going to equal a to the m plus n. The power rule says if we have a to the m to the n power, we're going to multiply those exponents. And again, the exponents are separated by the parentheses. So a to the m times n. Power of a product, we raise every factor inside the parentheses to the exponent. So a to the n times b to the n. Power of a quotient, a to the n divided by b to the n. The quotient rule, we're going to subtract exponents if we're dividing the same base. So a to the m minus n. Zero exponent, anything raised to the 0 power equals 1. The negative exponent, remember, we go on vacation, so a, or 1 over a to the positive n. In isolation, these are not too terrible. Where you will find yourself struggling probably is once we have to combine more than one of these rules in the same problem. So I'm going to walk through a few examples like that as we close out this video. We always want our answer to be written with positive exponents. Example 1. 4xy times negative 2x times 5x squared y cubed. Only multiplication is taking place here, so we can go ahead and multiply the coefficients. 5 times negative 2 is negative 10 times 4, negative 40. Now we can multiply the x's. X to the first times x to the first times x squared, and we're going to add those exponents to get x to the fourth. Y to the first times y cubed is y to the fourth, again as you add exponents. Example 2, very similar. 4 times 3 times 6 is 72. Y squared times y to the negative 10 times y to the 7th. We add exponents. 7 plus 2 is 9, plus negative 10 is going to be y to the negative 1. Remember, we're simplifying with positive exponents, so my final answer will actually be 72 divided by y to the first power. So that way the exponent is positive. Example 3, again simplifying with positive exponents. Sometimes it's helpful to go ahead and rewrite the problem pretty early, where we take care of the negative exponents first. And so if you choose to approach this problem that way, we would say 18a to the first times a cubed, since we'll bring this to the numerator, and b to the negative 6 will go to the denominator, so I would have 3b to the 6th, and then we bring down from the numerator b to the positive 6th in the denominator. At this point, we'll simplify up by taking 18 divided by 3 and getting 6. A to the first times a cubed. We add those exponents and get a to the fourth. That's going to be divided by b to the 6th times b to the 6th is b to the 12th. Example 4. Everything in the numerator is being squared. So we have 4 squared, which is 16. X to the 5th squared is now x to the 10th. Y to the first squared is now y squared. Z cubed squared is now z to the 6th. Negative 8. Often students at this point will be tempted to bring negative 8 to the numerator and make it positive using the negative exponent rule. But that won't work because 8 is not an exponent, and so that would be incorrect. A negative 8 is a negative coefficient. We do not move that to a numerator or to a denominator if necessary to change that sign. That sign is not changeable using the negative exponent rule. So negative 8 stays, x to the first stays, y squared stays, and z to the first stays. And I have these numbers, and each of the factors, the like factors, are kind of stacked into those separate fractions, even though it's still all 1, so that I can treat each thing separately. 16 divided by negative 8 is negative 2. X to the 10th divided by x to the 9th. Y squared divided by y squared, that is 1. And z to the 6th divided by z is z to the 5th. In example 5, in the numerator, 30z squared times z to the 5th. 30z to the 7th, because we're adding exponents when we multiply the same base, divided by 55 z to the negative 4. That we can move to the numerator to have z to the positive 4. We simplify 30 55ths by seeing that 5 is the greatest factor that goes into both 30 and 55, and so we simplify to 6 over 11. Z to the 7th times z to the 4th is z to the 11th. The last example we will do in closing. Why don't you go ahead and pause the video, give this problem a try, and then push play to see how you did. This entire fraction is raised to a negative exponent. And so I'm going to move everything from the denominator to the numerator and everything from the numerator to the denominator as I raise it to the 3rd power. So I'll start with the denominator. 10 cubed x cubed raised to the 3rd power as well is going to be the 9th power, and y to the negative 2nd power would move to the numerator and then back to the denominator because this is negative. So that's actually going to be a part of the denominator, y to the 6th. In the numerator, 5 cubed will go to the denominator. X to the 7th cubed is going to be x to the 21st. And y to the 4th cubed is going to be y to the 12th. I'm going to clean this up a little bit. 10 cubed is 1,000. 5 cubed is 125. I'm going to leave the x to the 9th for right now and the x to the 21st for right now. And I'm going to clean up the y's to be y to the 18th. Now again, I want to treat each set of common factors the same or separately. And I simplify the coefficients. 1,000 divided by 125, and we get 8. X to the 9th divided by x to the 21st. The way I like to look at these is I look at the difference between 21 and 9. And the difference between 21 and 9 is 12. And then I say which exponent was larger, the numerator or the denominator? In this case, the denominator. So that's where the answer will go, x to the 12th. And if what I just said makes sense to you, this might be a faster approach now that you understand the different rules. But to show you what would be happening there, x to the 9th divided by x to the 21st is x to the 9 minus 21 using the quotient rule, which gives you x to the negative 12, and then using the negative exponent rule, we're going to move that to a denominator and get x to the 12th. So this is the process using the two of the rules that we discussed in this lecture, and that's going to work every time. Again, what I choose to do at this point is find the difference and write my answer where the larger exponent was. If that's something that's helpful to you, great. And then y to the 18th just stays put. That's already been simplified. And there's our final answer. You will most likely need some more practice with questions like the last 6 problems that we've done, where the exponent rules are, you'll be using multiple of them in a given question. But again, take your time, pay attention to each specific detail, and you will be just fine.